sitting while over provisioned when you don't need them because it's spiky.
At the right time, it goes to 100% MFU, but only for a short period of time. And if that short period of time, you don't get all that over provisioned flops,
right?
Then during that short period of time becomes a long period of time.
And so what are you seeing for teams that are trying to optimize?
And flops are cheap. No, flops are cheap.
H100s are going up in price.
Well, not because of its flops, but because of H100. Hopper, it's bandwidth, its architecture, it's everything else, not just its flops.
So should we think about compute as not a scarce resource?
No, that's not the question. It's like this. When you ask about a car, back in the old days when we were unsophisticated, we used to say, how many horsepower is your car?
Right.
But these days, who does that?
So what's the right measure you think we should be thinking about?
Performance.
And what when you tell the teams, guys, this is the perf we got to hit next year, what are you finding is the eval you're reaching for more and more?
You have to come up with a real eval, a really serious eval. And because otherwise you'd be like improving your flops. You figure out something that you guys can improve, and you're improving that number. It doesn't make you smarter. You're improving that number. It doesn't make you more successful.
Yeah.
And so there's nothing wrong. There's nothing wrong with having a lot of flops. But it's not the complete necessary, not sufficient. That's all.
In one sense, you could think about the output of tokens as intelligence. So it should be some unit of intelligence per watt.
Yeah. And notice the tokens per watt is more than flops. And in fact, we know that now because for decoding these large language models, the single most important thing for generating tokens per watt is actually the aggregate bandwidth across the NVLink 72. And the MFU is incredibly low because the prefill is not that much. It's mostly decode.
But you can decouple decoding and prefill.
Yeah. It's disaggregated.
So
notice I just delivered incredibly high tokens per watt with extremely low MFU.
But not all tokens are born equal, right? And so how do we account for that? Like when you're designing the systems of the future, how do we account? What is the right way to measure without a standard measure of intelligence when you have coding tokens being more valuable per watt than, I don't know, some other kind of token? Does that question make sense?
Makes perfect sense. You always have to come back to not just optimizing for SAT scores. You're optimizing for something bigger. And so that's basically it. It's the same idea. You have to decide what evaluation. As you know, how you evaluate success matters a lot in how people perform. And so what NVIDIA does extremely well inside the company is the systems that we create for evaluating architectures, and flops is too contrived. Because it was that easy, then.
And so
I wouldn't be here.
You have a hard job, which is to try to design an index of different intelligences. Right? Because I think when our teams are researching on the NVIDIA architecture, we've got one lab doing coding, another one pushing the frontier of superconductivity and so on. And they all have completely different evals they're measuring for, but they're all using NVIDIA chips.
Yeah.
So how do you solve that problem when your customers all have their own evals?
Yeah.
But the architecture of the underlying platform.
That's why it's so hard. And here it is true. It's that hard. The problem is this: if you build something that's too overfit for something, you could be incredibly good at it. And so you're overfit for this one problem. You're insanely amazing at it. But then the problem is that market, that problem space may not be big enough to fund a sufficiently large R&D.
Right.
And so you want to be good at many domains, multi-domain. On the one hand. On the other hand, if you're good at everything, then you're good at nothing. You became general purpose. And so writing that balance, by the way, is artistry. That's what I do for a living. What should we not do? What should we double down on? What should we 10x on? That requires some amount of vision, strategy, some amount of trial and error, some just personal enjoyment and entertainment, iteration, all of that.
Can we talk about the canvas of Feynman, which is a chip I'm very excited about, but it's been hard to get info on it. What's the canvas telling you now about what your art piece is going to look like for the Feynman.
Well, I can tell you the journey that we came on. And so if you look at Hopper was designed for a problem space that was rather new. It was called pre-training. And so pre-training came along, and we came to the conclusion that although the generation before it was fairly significant already, that we should build even larger ones, tremendously larger ones, larger than any of the largest scientific supercomputers in the world. Okay, so that's a very big deal. That the largest supercomputer in the world was about $350 million, and we thought, you know what, pre-training is going to be such a large domain and such an important problem. We should design systems that could be multi-billion dollars. At the time that we're thinking about doing this, it just sounds insane. You know, you would have precisely 0 customers. And the reason for that is because the most expensive thing that has ever been sold was $350 million. And you're building something that's multiple billions of dollars. So you're building for a precisely a marketplace of 0. But we went and did it anyways on first reasoning. And so Hopper was designed for pre-training, and that was a great call. The second thing that we did was we said, okay, well, after training, we're going to keep making training better, but the goal is not of AI isn't training. The goal of AI is inference. And what kind of a system would inference really care about? And so we created a system called NVLink 72. And the reason we did that was because decode, in processing the neural network, there's the prefill, which is really context processing and things like that, and attention processing. And then the decode, which is generating all these tokens. The generation of the tokens requires really high memory bandwidth. And the amount of memory bandwidth you need is way more than one chip can possibly provide. And so we said, why don't we gang up like 72 of these things? And so we had to invent all kinds of new systems for switching and interconnects, and create all kinds of new SerDes. And we created essentially the world's first rack scale computer. It's called Grace Blackwell NVLink 72. The speed up over the previous generation, 50 times. In 2 years, we improved something by 50 times. Moore's law would have improved it by 2x. Okay. So the architecture and the insight was fantastic. And decode and inference and large language models and token generation, all of that kind of landed at exactly the time that Grace Blackwell came out, and boom, took off. So Grace Blackwell, another incredible generation. Now the question is, what happened to Vera Rubin, and what's the big idea? Well, the big idea is that the goal isn't just to think. The goal is to do work. And so Vera Rubin is designed for agents. And so the question is, what is the compute pattern? What is the processing pattern of agents? And agents, of course, you have to load a fair amount of memory, long memory. He's got working memory. So long-term memory, we put into storage, and we got that storage needs to be able to directly communicate with the GPU. You can't be copying the data off of the network storage, but you want the storage to be connected right into the processor itself. And so we have storage that's connected to the fabric. We're going to use a lot of tools. And so CPUs are going to be really important, but the CPUs of the current generation was really designed for cloud computing. And so you have these CPUs with hundreds of cores, 200 cores. Well, the CPUs of agents, because the AI is this multi-billion-dollar system, and it sends off an instruction to use a tool, and that tool is going to run on the CPU. Meanwhile, this computer, this GPU supercomputer, this multi-billion-dollar system is waiting for this one CPU. And so that CPU really wants to have extremely low latency. So we designed Vera, which is for current generation, for single-threaded, multiple core, single-threaded code. It is by far the most performant. And so we created a CPU just for that. Notice the way you solve this problem intuitively is you kind of think about, what is the computing pattern? How is it different than the past? You have to have some mental model about it, and you create a system that you can go and go build to run that. And so now agents are here. We're going to run that on Vera Rubin, and hopefully when Feynman gets here, it's going to be it's going to be like all software. We call them agents today, but it could be modules in the past or, sub modules. And so in the future, you're going to clearly have systems of agents and agents with sub agents and sub agents with sub agents. And so you're going to have, this swarm of agents and what kind of computer, does that manifest? And so that's likely what Flyment's about.
I have one more follow-up question on that, which is, one of the things you've always done well is kind of spot bottlenecks one generation ahead and then try to sort of pre-solve for them the supply chain. A year ago, that was photonics ended up becoming a huge solution. As we look at energy as a bottleneck, copper wires are one of the transmission sort of bottlenecks. How does that get solved in your view?
Energy is just everywhere. First, the first thing that we could do that is in our control, as with everything in life, whatever the problem is, whatever the external concerns are, you should do something that's in your control. And in our control is energy efficiency. So if you look at tokens per watt, we improved it by 50x, and then we'll have to keep on improving it by significant factors, and it compounds. So that's the first thing we can do. We can control that through co-design architectures and things like that. And the second thing that we could do, inspire people to, and that's through a lot of education, inspire the ecosystem to get ready for this. And I've been over the last half decade, helping people understand the amount of compute that's likely to be coming. And I just told you guys something about how I reason through how much energy is going to be necessary. The amount of energy that we need for computing is likely, probably 1,000 times more than we currently have. And that's an enormous amount of energy. However, the way to think about that is in the future, computers are going to be two things. It's always going to be generated because it's intelligent, it's contextually aware. So it's going to be generated. And then number two is going to be continuous. And so you've this generative computing in a continuous way, compared to pre-recorded retrieval based computing that is only initiated on, per use. The question is, how do you think about the amount of energy necessary for that? So I think if you say we need it 1,000 times, I wouldn't be surprised that we're off by a couple of orders of magnitude. And so we need a lot more compute. We need a lot more energy. And so you got to go and explain this to people. And so you got to explain it to people in a way that's kind of common sense and they can observe it, and there are, indicators along the way that in fact this is happening. And notice, just as I was breaking it down for you guys, reasoning about it for you so it's common sense to you. And so the amount of energy is high. And then lastly, the source of energy, there's all kinds of sources of energy, but unfortunately, because of great concerns about the cost of sustainable energy, we underinvested in sustainable energy. But this is the best time ever in the history of humanity to go and invest in sustainable energy. And the reason for that is because the market forces are so strong. Back in the old days, you needed government subsidies to go build solar farms and government subsidies to go build nuclear plants. And now you can just, market will pay you to do it. And so market forces are so powerful right now. This is our best chance to upgrade our grid, our, archaic grid, add sustainable energy of all kinds. And, this is a great time.
In terms of education, what I've learned as well, we designed the class for the students here. Turns out a lot more people, especially a lot of investors and capital allocators, are watching this.
Oh, is that right? Oh, shucks.
Let me put it up. Yeah. And so